Hello, Professor Rajesh. Gopkumar, you can hear me? You have to unmute.
Hello.
Hello, Professor Rajesh Gopkumar.
Yeah, hi.
Oh, nice to see you. Nice
to see you. And that's Professor Ambika also, right?
Yes,
yeah.
You can also see.
Yeah.
Hope you had no problem in joining and.
No, not at all. I will check my slides. I'm sure that will also work out.
Would you like to just check your slides now?
Yes, I will do that right away.
Maybe I think we can just very quickly see before the other events start.
Exactly.
You can share your presentation and to make sure that it is.
In fact, I have 1 or 2 animations, so I'll just check whether those are working. Just 1 second. So is my screen visible?
Yeah, I think we can see.
You can see it.
You can go to full slide mode.
Okay, right.
Yes, very good. Yeah, good. You can also, forward and all that. Yeah, it's working.
Yeah. So let me check. I have something with an animation. So let me play that and see whether. Okay.
It's coming out.
Okay. And just 1 more slide, I think, which has an animation. So I'll just play that. Okay.
It's also working.
Okay, great. So, yeah.
Thank you.
So that I think is the thing. I'll stop sharing.
Okay, that's good. Thank you.
Not at all. How are you?
Yeah, things are fine. Things are fine. So we're all getting back to in-person mode slowly.
Yeah.
I'm sure the same thing with your institute also, perhaps.
Yes, absolutely. And we were, all our programs had become suspended, or rather in online mode. And now we are slowly going back to hybrid mode, even for the meetings which have people from outside India and elsewhere. So, yeah.
Yeah, we are all so used to online mode. Even if you call people in person, they take time to come. They have lost
right.
having in-person meetings.
Yeah, the thought of going to in an aeroplane and everything becomes a little bit daunting now.
We'll certainly have you sometimes, spending a couple of days in the institute.
Absolutely.
It'll be nice for you to interact with our students.
Yeah, no, I would love to. I enjoy, of course, I think, as you know, in Pune also, when I was this thing, I was very happy to come and interact. And
this is our transit campus where we started.
Okay.
But our main campus, we have about 300, 350 students there.
So they'll
be joining. It's about 25 kilometers away.
We
are beaming this lecture there, and so they will all be sitting in a hall there.
I see. So you are so classes are happening in the main campus?
Yes, we are in a hybrid mode. When we teach from here, students join online from there, and vice versa.
I see. So the lecture theaters there are not yet complete.
Not our main building. It will take at least 1 year. But right away we have an undergraduate lab block. I think we'll show a very short video of that.
Okay.
And our laboratories are ready, undergraduate labs only, not the research labs.
Okay.
And it's just enough for us to go for another year and a half.
Okay.
because this place is saturated now. We won't be
I
able
see.
to accommodate anymore.
Hmm.
A lot of our research activity is here. There
I
we are
see.
only running undergraduate practicals and classes.
Okay. And the hostels,
First year, second year, third year. Yeah.
And the hostels are also there.
Yeah, we have a 500 capacity hostel here on the transit campus, and
Okay.
about another 500 capacity hostel in the main campus.
Nice.
Yeah, by about July, so another 600 capacity hostel should be available, in the main campus.
I see.
So we are given certain priority and, step by step, because everything will not happen in one go. Stage wise, we will slowly shift.
Okay.
Yeah. The main logistics is we are 26 kilometers away. So
From
we need
the-
to, the faculty have to go, sometimes students have to come. So this mobility and
Yeah.
with a railway crossing in between, sometimes
Oh,
it takes
I
little
see.
time.
I see. So the main campus is in a rural area. It's a sort of
It is a village. It is a village. It's at actually there are 3 villages. The land has been, it's trifurcated between 3 villages.
I see. I see.
But all our land acquisition formalities, they're all over. In fact, campus construction is in advance. About 50% has happened already.
Okay.
The staff quarters are getting to ready. Students' hostels are getting ready. And lecture hall also, we would like to get it by August. These are our priority, but the main academic block with research facilities will take some time, at least 1 year, or 1.5 years even, because we have to furnish them with a lot of laboratories, etc., etc. So that will take time.
That always takes a lot of time.
Yeah. Maybe I could just introduce my colleague. Of course, Professor Ambika.
Yeah, Ambika.
And I don't know whether you have met Professor Nagraj, D.S. Nagraj. He is mathematics.
Okay.
He was at math science before.
I think we may have met before in math science. I think. So how many faculty are
A couple
now?
of my other colleagues are traveling or they have not come. I think, but the students are slowly joining.
Okay.
So we'll take about 10 minutes or so to actually start the event by 11 o'clock.
No problem at all. Now, how many faculty are there in ISER?
We have now 51 faculty.
Oh, that's a lot.
Yeah, 51. But our students are close to 950.
Okay.
So compared to the students' number, faculty, that ratio we are 1 to 20 almost.
Yeah. That's.
So, Mr. Rajesh, this is Dr. Mohan Kumar, our registrar.
Okay.
Yeah.
Hello.
Yeah, he was started with Institute of Science, Bangalore. Then he was at University of Hyderabad as registrar. Then he was at TIS, Mumbai. And from there, he came over here.
Okay.
Good
to see. Yeah.
So, but another 6-7 minutes or 10 minutes.
Yeah. Okay. No problem. I'll.
So we'll play a short video. Just gives you some idea. You make a full screen. Full screen and start again. There's some music also now.
Good morning to all. A very warm welcome to the celebration of the 7th Foundation Day of ISER Tirupati. Special welcome to our Honorable Chief Guest, Professor Rajesh Gopakumar, Director ICTS Bangalore, members of the Board of Governors, Finance Committee and Senate, students, staff and faculty at ISER Tirupati, and all others joining online. I request those who are joining online to mute their microphones, and also those joining in person to keep their cell phones in silent mode. Thank you. We will now begin the program with introductory remarks by Director Professor Krishna N. Ganesh. Over to you, sir.
Good morning, everyone. Professor Rajesh Gopakumar, today's chief guest. ISER students, faculty, staff, and other invitees. I welcome you all for the 7th Foundation Day lecture. It was on this day, on 28th March 2015, the foundation stone for ISER Tirupati was unveiled by Srimati Smriti Irani, the then Human Resource Minister, along with that of IIT Tirupati and IIIT. The first batch of 35 BS-MS students in 2015 has now grown to 697, along with 129 PhD students, 60 integrated PhD students, and 30 postdoc students. Altogether, 920 now in academic residence at the Institute. We have a faculty strength of 51, administration, engineering, and support staff of 49. This is our 7th Foundation Day. We always had distinguished Foundation Day speakers to address us and inspire us by their own eminence and achievements. The previous speakers were Professor D. Balasubramaniam, a well-known physical chemist in 2016, Professor Dipankar Chatterjee, a biophysicist in 2017, Professor Ajay Sood, physicist, 2018, Dr. S. Shivram, a polymer chemist in 2019, and Professor G. Rangarajan, mathematician in 2021. Due to a pandemic, the 6th Foundation Day could not be held during 2020, on which Dr. Chandrimasa, immunologist, was supposed to be the speaker. On Foundation Day every year, it is customary to recall the highlights of the Institute during the previous year. During academic year 2021-2022, many of our students and faculty have made us proud by their achievements. Dr. Vijay Subramaniam, Assistant Professor Biology, was awarded the Wellcome Trust Intermediate Fellowship. Dr. E. Balraman and Dr. Aravindan, Assistant Professors in Chemistry, received MRSI Medal and Lecture Prize recognitions, respectively, from Material Research Society of India. We happily note that Professor B.J. Rao, who was Chair of Biology, was appointed as Vice Chancellor of Central University of Hyderabad. We are also very delighted that Professor Ramesh Sonti, a distinguished plant scientist, well recognized for his transformative research in Samba Masuri rice, has joined as Chair of Biology at ISER Tirupati. Under his leadership, we have established a Center for Excellence in Plant Sciences, which is already functioning from main campus. Shubhra Singhal and Shreyas Parki from ISER Tirupati, 2 students, with Komaresh Krishnan from Harvard University, received Seed for Change grant from Mittal Foundation for their project, boosting natural immunity during a pandemic. They were jointly mentored by Professor Venki Murthy, faculty at Harvard, and Dr. Vasudha Rani Devanathan from ISER Tirupati. The ISER Tirupati IGEM team won 3rd consecutive gold medal in 2021 for their project, OV Cloak, a novel contraceptive for uterus owners. I was just informed yesterday that ISER Tirupati students team has won 2 top prizes this year in the highly competitive Mimamsa which is an intercollegiate national quiz competition organized every year by ISER Pune. The ISER Tirupati team, consisting of Sanskar Agarwal, Rajashri Umbarkar, Anhad Bagga, and Nachiket Subhashri. They had the zonal topper prize for AP zone, and also Sanskar Agarwal was the subject runner-up for mathematics. Last year, our student Tamarai Valli had bagged the same prize, clearly indicating ISER Tirupati student strength in mathematics. Akshay Nair was selected for Fulbright Nehru doctoral research program to work for 9 months in a US host lab, collaborating with Dr. Annapurna Devi and on epigenetic inheritance and stress memory. Today morning, I got to learn that our student Purva Atul Naik got selected for the Max Planck Institute Germany internship, a master's thesis internship. And this student was mentored by Dr. Annapurna and Dr. Srinivas Shavli. I must say that ISERs have a joint MOU with Max Planck Institute Germany. A total of 7 PhD students from ISER Tirupati have so far been selected for the prestigious Prime Minister Research Fellowship Award, PMRF. The second convocation of ISER Tirupati was held on 24th August 2022 with Dr. K. Vijayaraghavan, Principal Scientific Advisor, Government of India, as a chief guest. And the convocation was presided by Professor J.B. Joshi, Chairman, Board of Governors, ISER Tirupati. About 64 students received BSMS degree and 1 student received BS degree. We are delighted that the first 2 students of ISER Tirupati have submitted their PhD thesis recently with a work done here at Tirupati. The ENS France and ISER meeting on pedagogy practices was held during May 10th to May 11th last year with participation of several ISER and ENS faculty. The ISER IIT Joint Research Initiative, Center for Atomic, Molecular, Optical Science and Sciences and Technology, CAMOST, held its first joint meeting on collaborative research progress in August 2021. The Tirupati Education Cluster was launched with joint participation of ISER, IIT, Sri Venkateswara University, and Sri Padmavati Mahila University to focus on designing and sharing of courses, organizing training workshops for PhD students, collaborative research, joint activities on community connectivity and public outreach, and setting up incubation centers, startups, and also for tackling local, societal, and environmental and ecological issues. On Science Day this year, February 20th, 2022, Professor Ganapati Yadav, former Vice Chancellor of Institute for Chemical Technology, ICT, Mumbai, gave a very thoughtful lecture on important role of science and technology in sustainable development, particularly focusing on hydrogen economy and circular economy. ISER Tirupati signed an MOU with University of Melbourne, Australia, on initiating joint PhD program. During 2021-2022 financial year, the faculty at ISER Tirupati have received 18 extramural projects from various funding agencies to the tune of 13.8 crores rupees, including 2 projects from industry. I'm very happy to inform you that just last week, the institute received sanction of rupees 10 crores from DST for establishing the first BSL-3 facility in Andhra Pradesh. This will enable our research in infectious diseases such as tuberculosis and viral diseases. ISER Tirupati has organized several science-related activities, workshops, research seminars, and outreach activities under Azadi Ki Amrit Mahotsav program on the eve of India's 75th independence. Today's event is also another important event under this banner. In December 2021, the new undergraduate laboratory block and the 520 capacity students hostel became functional with 300 students residing now, and the academic activities also pursued from the main campus. You saw a video of this just a while ago. The setting up of these facilities at 25 kilometers away from transit campus was possible due to hard and dedicated work from technical and administration staff under the pandemic situation. IISER Tirupati published 131 research papers in 2021 and already has 40 publications till now in 2022. Many of these include high-impact journals such as ACS Energy Letters, Journal of American Chemical Society, Organic Letters, ACS Chemical Neuroscience, Physical Review Letters, Gene, Plant Molecular Biology, Nature Chemistry, Nature Communication, etc., to name a few. We have now crossed the number of research papers beyond 500 since the inception, which is very, very creditable for a new institute just in its 7th year. With these highlights about the institute in 2021-22, I end my remarks, and I hope that 2022 will see even more rapid rise since all our BSMS students, except for 2021 batch in PhD and PhD students, are all back on the campus with invigorating energy, raring to go fast to compensate for the 2-year absence due to COVID. I wish to thank all the institute members to make these achievements possible, and also sincerely thank our Foundation Day speaker, Professor Rajesh Gopakumar, for his time for us on this day. Thank you very much.
Thank you, sir. The chief guest of the day is Professor Rajesh Gopakumar, Director, International Center for Theoretical Sciences, ICTS, Bangalore. To introduce the chief guest, I invite Professor Gauri Ampika, Coordinator Academics and Chair Physics Discipline.
Good morning to the chief guest of the day, Professor Rajesh Gopakumar, who has joined online on the screen, and all other invitees who have joined us on this special occasion on the screen. And very good morning to all of you who have assembled in this auditorium to celebrate the 7th Foundation Day of our institute. It's my it's my pleasant duty today to introduce the chief guest of the day, Professor Rajesh Gopakumar, who is current Director, International Center for Theoretical Sciences, Bangalore. He's a well-known theoretical physicist in the very challenging area of quantum field theory and string theory. Professor Rajesh Gopakumar did his basic degree in physics from IIT Kanpur and completed his PhD at Princeton University under the Physics Nobel laureate Dr. David Gross. As a graduate student, he not only excelled academically, but also outshined his batchmates as a long-distance athlete, weightlifter, and a footballer, a very rare combination. After a brief period as research associate at Harvard University, he moved to Harish Chandra Research Institute in Allahabad in 2001 as associate professor and then professor till 2015. He joined ICTS in 2015 as senior professor and is now the center director since then. He's also a visiting long-term member at the Institute for Advanced Study Princeton from 2001 to 4 and an adjunct faculty at IIT Kanpur, TAFR Mumbai, and an honorary professor at JNCASR Bangalore. Professor Gopakumar's research is basically at the intersection of quantum field theory and string theory, focused on deciphering the ADS-CFT correspondence. With around more than 70 journal publications, he has established his mark in this highly mathematical and abstract branch of theoretical physics. He is well known for his work on different aspects of string theory, such as topological string theory, gauge string duality, non-commutative field theories, large and limits of gauge theories, higher spin theories, etc. Most notably, along with Kunbrum Wafa, a string theorist at Harvard, he introduced a series of new topological invariants now known as Gopakumar-Wafa invariants. These lead to a generating function for another set of invariants named after Gromov and Witten. Naturally, the scientific community has recognized his achievements in several ways. To list a few of his awards, he is the recipient of the Distinguished Alumnus Award from IIT Kanpur in 2019, the World Academy of Sciences Award was for Physical Sciences in 2013, G.D. Birla Science Award in 2013, and Fellow of the Global Young Academy of Scientists in 2010, Shanti Swarup Bhatnagar Award in Physical Sciences from CSIR Government of India in 2009, Big Prize of the ICTP in 2006, Swarna Jayanti Fellowship in 2006, and B.M. Birla Science Prize in Physics in 2004, to name a few. He is also a fellow of all the Indian academies, Indian Academy of Sciences, the Indian National Science Academy, and the National Academy of Sciences, India. He was elected the fellow of the World Academy of Sciences to us in 2015. He is a founding member of the Global Young Academy GYA, which is an initiative by TOS. His presence is very well felt in all conferences in string theory and related areas around the globe. He is a frequent speaker and resource person in many workshops related to string theory and well known for explaining deep mathematical results in a very lucid style. Today, he will talk on why strings, a question he must have been asking himself since he started research and presumably has found an answer. He will share that wisdom with us today. With this brief introduction, I invite Professor Gopakumar to deliver the 7th Foundation Day lecture at ISER Tirupati. Thank you.
Thank you, Professor Ambika, for a very nice, kind introduction. Also, it is a pleasure to hear from Professor Ganesh about the wonderful journey that ISER Tirupati has been on. And I'm sure under his leadership, it will really flourish. ISERs have a very special place in my mind. I think they have really changed the landscape of Indian science in a very fundamental way. To be interacting with the young students of ISERs is always a great pleasure. And I hope in person at some point I will definitely have the chance to come and interact with all of your faculty and students there, and see the new campus also coming up, of which I just got a glimpse on the video. So thank you very much for inviting me to be with you on this very special occasion. The Foundation Day is a time to take stock, and as you just heard from Professor Ganesh, it is, I think, ISER is clearly has many things to be proud of, and I'm sure it's a collective effort of the students, the faculty, the administrative, scientific, technical staff, and of course the leadership. So my best wishes for the years to come. So as Professor Ambika mentioned very nicely, I think I titled my talk as Why Strings, because it is perhaps a question, indeed, something I have also asked myself, but also a question perhaps many of you students, faculty, others who are not in this area might have thought, yes, you hear about the string theory, what is this thing, and why do people talk about strings? After all, we understand mostly when we learn physics or chemistry and so on, we think of point-like particles. We have atoms, we see that they have subdivided into further point-like particles, protons, electrons, neutrons, or perhaps quarks, etc. So why strings? So what I will try to do, and let me share my screen, just 1 second. So what I will try to do in my talk is to give one potential answer to these questions, and at least one direction, which I think might strike a chord with many of you, because it is what I would like to say is that this notion is very rooted in a lot of the physics that all of you, even the first year undergraduates, all of you have studied and are familiar with. So I'll try to embed this in a broader historical context and explain to you why the concept of strings is so natural, and towards the end I will try to give you a little bit of a glimpse on some of the very novel ideas that have come out from pursuing this from pursuing this direction of string theory, how it has connected with many fundamental aspects of physics. Okay, so let me start. It's quite a remarkable thing that all the forces that we see around us are, in the end, manifestations of four fundamental ones, namely the gravitational force, which all of you know about, the electromagnetic force, which we slowly learn in school and through the undergraduate years, and then two forces which are probably less familiar, but maybe all of you have heard about them. One is the strong interaction, which are effectively the nuclear interaction, which is what keeps the nucleus of an atom together, overcoming the repulsion, electromagnetic repulsion of the protons. Something has to be keeping the nucleus together, and this is the strong interaction, much stronger than electromagnetism, which has now description at the quantum level, which goes by the acronym QCD, or quantum chromodynamics, about which I'll say more later. And then there is also something whose the phenomena is familiar to all of you, that of radioactivity, which is mediated by the so-called weak interaction, which has now, thanks to the work of Glashow, Weinberg, and Salam, been unified with the electromagnetic force into what is called the electroweak interaction. But because they are sufficiently different, we kind of still think of them as two separate interactions. Now, there's a very fascinating story, and many of you might have heard about how we as scientists have deciphered the nature of these forces, and many of these go back for centuries. But there's a second fascinating story about how we have understood their manifestations, which even now we see in multiple ways, and we are still unraveling. And I'll probably say things about the gravitational force, which we are still trying to figure out. So it is so just knowing that these are fundamental forces is not enough. We are still working out all the manifestations of these forces, and even something like the electromagnetic force gives rise to all the very complex materials, the chemistry, and so on and so forth. So it is very non-trivial how these forces really show up in nature. So, as I said, I'll try in this talk to say why strings naturally arise in these descriptions. Now, when people often give a talk on string theory, they usually focus on gravity and quantum gravity, but I want to take a slightly different route. So I'll say a little bit about gravity and come back to it at the end, but this will not be the focus of my talk. But just for completeness, let me just say, of course, that all of you know gravity is the most apparent force in nature. We all feel it very in our bones in some ways. And Newton's genius was that he came up with this law of gravitation, which you have all encountered from high school. And in some ways, it was the first universal law in physics applying to motion on Earth, applying to the motion of planets around the sun, and the Earth around the moon around the Earth, and of course at that time we didn't know about things outside the solar system, but gravity is a universal phenomenon, as we now know. But Newton's law was very accurate and worked, and we know it is good enough for even for the rockets that we sent out and for most purposes. But when we go to the larger cosmos, we learn that ours is a relatively sort of placid part of the universe, but there are extreme phenomena out there in the universe for which Newton's law is only approximately true. And to really understand a lot of that, we need Einstein's overhauling of the law of gravity, and whose basic message is that the force of gravity is encoded in the geometry of space-time. I will come back, as I said, to this maybe towards the end, but as I said, my main focus will not be on this, but just for you to keep in mind that our best understanding of gravity is the Einsteinian one, in which gravity is encoded in the geometry of space-time. But I want to start the story in a sense with electromagnetism, which is for many of you as even undergraduates, you come to learn a lot about electromagnetism and how it is in a way the interaction which is responsible for most of the complex arrangements that we see around us in nature. The different phases of matter and the different materials and their properties and so on. And it was, of course, the triumph of 19th century physics that the seemingly different electric and magnetic forces were unified by Maxwell, and building on the ideas of Faraday and others, and it culminated in the Maxwell equations of 1860s or so. And this was spectacularly borne out by the experiments of Hertz, who showed that light is indeed a form of electromagnetic wave, the electromagnetic field, so to say, propagating in a wave-like oscillation, which is created by accelerated charges. So that was one of the triumphs of Maxwell's equations. And of course, all of you have studied some of this, but I want to emphasize a certain point, which perhaps is not so familiar, because after all, we don't hear so much about the things of the 1860s. But what I want to point out that in electromagnetism, actually, there are two pictures of classical electromagnetism. And we often focus now on the field picture of Maxwell, which is in terms of an electric field or a magnetic field at every point in space and time. But historically, actually, Faraday had thought of electromagnetism in terms of lines of force, and all our books, of course, have some initial drawings about these, but very quickly you move on to these field picture. But I want you to dwell a little on this. I will sort of try to say that this is actually, in some ways, this is a very important distinction, as we have come to appreciate in recent times. So the distinction is, as I said, between these localized point-like fields, the electric and magnetic fields. So at every point in space, x and time t, there's a vector, electric field vector and a magnetic field vector. But here you have these lines of flux which end or begin on the different charged particles and sort of spread out through space, but give you, I think, a very intuitive picture of the strength of these fields. And Faraday's insights came from this lines of flux. And it perhaps is not so much appreciated that this Faraday's picture of the lines of flux was very important for Maxwell. In fact, Maxwell struggled, and I have looked at some of his old papers of the 1860s. It's very nice to go through them. He struggled to write down equations for these lines of force. So he spent almost a decade, I think, trying to write down equations, because that's how people understood electromagnetism, and Faraday's picture was really very compelling for him. So he was trying to think of these lines of force as sort of flux tubes or vortex like tubes of some incompressible fluid. So you can think of this very roughly as if there is some fluid of some kind flowing, and these are like some tubes of these flows. So he tried to write down mechanical equations describing these tubes, and which he thought would capture how the lines of force behave, what is the dynamics of these lines of force, which is what he was trying to uncover. But finally, he realized, and this was his, I think, the genius, that the description is much easier in terms of these vector fields, these electric and magnetic fields. And then he wrote down the Maxwell equations, of course, not quite in this form. This was introduced later by Heaviside and others, but this is one of the very succinct ways in which now you see in your first year undergraduate physics course. And this, as you know, is behind a lot of the, from the 1860s, much of the modern industrial world was built on the foundations of these equations. So I say the rest is not history, but is modernity. So you have seen these equations, but now I want to so this was just keep this in mind about this, how this two different pictures and how Maxwell struggled with them and finally wrote down these equations for these fields. But soon afterwards, in the late 1800s and early 1900s, there was a major puzzle, which was the fact that people learned about the existence of stable atoms in which there were charged electrons around the nucleus. And this posed a major challenge to the Maxwell's theory, because Maxwell's theory told you that the electrons, when they're moving around in an orbit, they're accelerated and therefore will radiate and therefore will lose energy and therefore will spiral into the atom, the nucleus, and there wouldn't be any stable atoms. And at the same time, the photoelectric effect was understood by Einstein in terms of a particle-like character to light, which seemed to go against a lot of the experiments on diffraction and so on, which exhibited a wave-like particle, wave-like nature, character to light. And in a way, I like this little cartoon. If you see, this shows light is a particle. If you see particle, but also wave. If you look at it another way, you can't simultaneously read particle and wave, and so you have a particle and a wave description of light. So it's this dual nature which was also very difficult to understand in the Maxwell's theory, and this was reconciled, and perhaps many of you have taken some courses, at least on modern physics or quantum nature of physics, which says that there is a wave and particle dual nature to not only light and electromagnetic waves and so on, but also to electrons, protons, and other so-called particle. And this was at the heart of the then theory of quantum mechanics that was developed by around 1925. But modern day theoretical physics, quantum mechanics is of course very underlies it, and we still see no reason to doubt it as the framework underlying underlying nature at the very smallest scales. But the quantum mechanics, in some sense, had its most comprehensive framework, which unified wave and particle duality in terms of this theory we now call quantum field theory, which unifies wave-particle duality by thinking of fields. So now you are kind of bringing together the Maxwell concept of the field and the quantum concept together, so that you can both incorporate the oscillations of fields that like electromagnetic waves, but also you can think of them in terms of localized excitations. And this movie over here is a nice simulation of, in a sense, how quantum fields in the vacuum really are behaving. So this is in some sense trying to show you, give a mental picture of the fluctuations in the field, which you can think of in some contexts as particles, and in some when they're localized, but in other contexts when they are delocalized as waves or oscillations. So this framework of quantum field theory was first developed, and because when you needed to develop it actually because you want to understand not just atoms, but how do electrons interact with the electromagnetic field? How do you consider the electromagnetic field of Maxwell at the quantum level? And this led to the theory of QED or quantum electrodynamics, which was very successful. And many of you may have seen this, but I really want to emphasize to many of you who are young scientists that this is a true triumph of the scientific method. There is a quantity called the anomalous magnetic moment of the electron, which has now been measured experimentally to about 11 decimal places with then some error bars, and these are the error bars. And at the same time, there is a scheme to use quantum field theory and calculate in better and better approximations, so-called perturbation theory. And you can again calculate to 11 decimal places, again with some inaccuracy on the effects that you have not taken into account. And you can see the spectacular agreement between these two numbers. So this is really when you see this, you see this. Science is not some kind of just words and talk. It is real, where you can match theory and experiments to so this is in some sense the high point, I would say, of the scientific method. In any case, let's come back to the old description, the contrast I was making between the Maxwell and the Faraday picture. So one reason for this enormous success, the matching that I showed you in the previous slide, this enormous success of QED, and by the way, this is only one of many experiments, many quantities that have been matched. So no wonder QED, quantum electrodynamics, is considered one of the best, most precisely tested theories. And this is the one for which Feynman and Schwinger and Tomonaga got the Nobel Prize. But a reason for its success is that the strength of the interaction is quite small. And what is the strength of the interaction? We know that electrically charged particles interact because of the charge. So it's the product of the charges of the two charged particles. So the fundamental, if E is the fundamental unit of the electromagnetic charge, then there's an appropriate dimensionless object involving the Planck's constant and the speed of light, h bar and c, which effectively measures the strength of the electromagnetic interactions. And this is a famous number, which is approximately 1/137. You can see it's about 0.01 or so. So it's quite small, and you can the quantum effects are therefore small. This is also a measure of the quantum effects in electrodynamics. This is why Maxwell's theory is good enough if you want to make a dynamo or do your experiments in your lab of Maxwell's, Faraday's experiments and so on. It's the classical Maxwell equations are a very good approximation, and the quantum effects are small, and the classical description that you learn in your physics 102 or whatever course it is in terms of electric and magnetic fields is a very good first approximation. But then you can go beyond, and that's how you get some of those corrections of the kind that I showed earlier. But this also gives you actually an insight into why Maxwell did not succeed in writing down equations for those lines of flux, because it turns out, and one can see this more in hindsight, it's not perhaps so obvious right now when I say it, that these lines of flux are really very loose and kind of very floppy, so to say. And this is reflected in the fact that you see when I have a positive charge and an electric charge, the lines of flux extend all the way to infinity. So they're kind of very, very spread out and very floppy is, I guess, my mental picture, that you don't have a very rigid kind of a line of flux. Whereas you remember I mentioned Maxwell was trying to write down, think of these as some tubes, vortex tubes of things that are flowing, but it's not quite like that. There are no rigid tubes over there. And that's because the lines of flux actually spread out all over, and in some way ultimately it can be traced to the smallness of this interaction that governs the interaction. But now let me pivot to the other force that I had mentioned, the strong interaction, which is what we use to describe the force that holds the nucleus together. And this at first sight looks very different from electromagnetism. It acts on the quarks which make up protons, neutrons, etc. It's much stronger than electromagnetism. In fact, the force grows with the separation, unlike in electromagnetism, where as you separate the two charges, the force becomes weaker, smaller. Here the force grows with separation and in some sense confines the quarks into the nucleus. And we have now a lot of experimental evidence for many of these things, that the behavior of the strong interactions is quite different from electromagnetism. But there is nevertheless a picture which is very close to the Faraday picture. Namely, you can think of the lines of flux between a quark and an anti-quark, the corresponding things to a positive and negative charge. You can think of the lines of flux. Now they are kind of collimated. They are bundled up into a string-like tube. And this is actually a simulation of the equations of QCD, a computer simulation of the equations of QCD that you see on the bottom right, which shows how when you separate out, say, two quarks, how the lines of flux behave. There are arrows over here which you may not be able to see, but they effectively show how the field behaves near the quarks. And you see this, and the energy, there's this plot, the vertical axis is sort of the energy density, and you can see there's all the energy is sort of concentrated in this tube between the two charges, unlike the electromagnetic case. And in fact, it's not, in fact, despite the very different manifestation of the way in which the forces behave, the QCD is described by a very beautiful generalization of Maxwell's theory, what is called a Yang-Mills field theory, or more accurately, a Yang-Mills quantum field theory, because it really is the quantum nature of the field is very important, as I'll say in a moment, for the behavior of these quarks. And this called quantum chromodynamics for historical reasons. But one phenomenon which is sort of a close analog in electromagnetism to this picture you have here is, maybe some of you might have seen, you have taken physics courses, something in superconductors called the Meissner effect, where if you try to turn on a magnetic field through a superconductor, it normally tries to be expelled, but if you increase the strength of the magnetic field high enough, it will penetrate the superconductor, but in thin vortex-like tubes, very much like Maxwell's vortex tubes, actually. And this is in fact called the Meissner effect. In some ways, in QCD, it's as if the vacuum is like a superconductor and the Meissner effect is in play. That's in some ways a qualitative way of understanding why QCD is so different from electromagnetism. In some ways, it's the difference between a superconductor and a normal conductor with respect to the behavior of magnetic fluxes, etc. So there is this beautiful theory we understand called QCD, which in 1974, Professor Ambika mentioned David Gross. So this was one of the results. David Gross and his student Frank Wilczek and Pulitzer, they uncovered the field theory that is responsible for the strong interactions. Before I continue, I just want to share this statement which I found by Paul Dirac, one of the founders of quantum mechanics and one of the most influential physicists of the 20th century, the most remarkable physicist. he wrote in 1956, much before something like string theory and all were even thought of. He wrote that, and he was actually, even before we understood the strong interactions, which I said in 1974, this was 1956 when he was actually thinking of electrodynamics at the quantum level. He had this picture, which is very prescient. He says, when we may assume that when we pass to the quantum theory, the lines of force of Maxwell or Faraday, basically they become all discrete and separate from each other. We now have a model in which the basic entity is the line of force, a thing like a string instead of a particle. The strings will move about and interact with one another according to quantum laws. So this was a very profound insight, I think, that Paul Dirac had at that time, even without knowing anything about the strong interactions, where you actually see the string really taking a real form. I said in Maxwell's theory, it's very floppy, but he still intuited that the string is somehow a very a basic entity to be considered. And so this is sort of one way to sort of motivate why the string like excitations are very natural. But coming back to the Yang-Mills theory or QCD, the strongly interacting Yang-Mills theory, like because they kind of confine, like I said, they are very difficult to solve using the techniques that work for QED. And essentially it is because the corresponding strength of the interactions, which I showed you was 1/137 in electrodynamics, this is of order 1 in the strong interaction. So instead of alpha electromagnetic, now I'm considering this alpha strong, the strength of the strong interactions, and it's a dimensionless number of order 1. So the quantum effects are substantial. And this is in a sense why there's one way to understand why the Faraday lines of flux picture is very useful. You actually have somewhat more rigid lines of flux, like I showed you, and I showed you that computer simulation. So this is where the Faraday picture is potentially very useful, but then we have to go back and try to revisit Maxwell's approach. Can we write down equations for the dynamics of these strings? And in fact, people studied in the 60s and 70s the bound states of quantum chromodynamics, which are the simplest ones are these so-called mesons, which have a quark and an anti-quark. And these, if you look at there's a whole zoo of mesons, but if you look at their systematics, they seem to be very close to the excitations or the harmonics, the different vibrational modes of a relativistically moving free string. So that gave yet another reason to believe that in understanding QCD, there is an underlying string-like picture, because if you plot the masses versus the spins of these mesons, they lie on a straight line, which is what you would get if you thought of them as excitations of a relativistic string, a free string. But there were some other pitch properties of QCD, the detailed properties of the interactions, that disagreed at least with this simple string picture. So this is why people felt there must be a string-like picture, but they couldn't quite pinpoint it. And so even though everything suggested that the Faraday lines of flux picture must be somehow applicable, one couldn't really find these equations. And one of the things was that one of the aspects here was that in some sense, the QCD string appears to be a fat string. The picture that I showed in the simulation, you might have seen, it's like a very fat, thick string in some sense, in nucleus units. The scale over there is the nuclear size. So it's a detail. So the detailed properties are quite different from if you think of an idealized thin string or a kind of a fundamental string, in which, like a fundamental particle is point-like and has no extent. A fundamental string has only an extent in the longitudinal direction along its length, but no thickness. So the detailed equations seem to be very different when you try to understand write down equations that would describe, and this is at the heart of some of those discrepancies I mentioned earlier. So it seemed as if one was at an impasse because, well, I mean, there is this nice physical picture, but it doesn't really give you the mathematics to describe the behavior of the strings. I mean, it captures some part of it, but not quite everything. So the amazing thing in the last 25 or so years has been this thing that was the mysterious term that came up in Professor Ambika's introduction, the ADS CFT correspondence. I'll say a little bit about it to give you a flavor in the last 10 minutes of this talk about how this has given a completely novel insight into this whole question, for which I think I've given you the historical background to appreciate the question. So this these insights due to an Argentinian physicist, Juan Maldacena primarily, they suggest that these QCD-like strings, the strings in QCD-like theories, they obey equations of idealized strings, these fundamental strings, not in four-dimensional space-time, but in a five-dimensional space-time. So you might think that's completely absurd, but I mean, you're describing your nuclear physics behavior of quarks and so on in your ordinary space-time. You may be far from any gravitational field. Why are you talking about some five-dimensional curved space-time? In fact, the space ADS refers to this curved space-time called the anti-de Sitter space-time. It's some kind of a hyperbolic space-time. So you might think, what is what does this have to do with anything? So just bear with me a bit, but let me explain why having this, if you allow yourself to think, so to say, into an extra dimension, how it actually resolves a lot of the puzzles that were there earlier. So I said one of the points was that there was this thick string. You see, I've drawn a thick string, but you see a thick string can be a shadow of a thin string. When you kind of project a thin string, an idealized string in 4 dimensions in this way, and this is why this is sometimes called a hologram, that you think of this as some kind of a screen for your 4-dimensional space-time, as some kind of a screen, which is like a boundary or a end of a 5-dimensional curved space-time, this anti-de Sitter space-time, and you think of a 5 string in that 5 dimensions, its shadow, in some sense, the thing that you actually see will be a flux tube, which has the same kind, which has this sort of thickness, and the thickness is kind of determined by how far inside the string is moving. If it is very close to the boundary, it will be very thin, but if you go, as it goes more and more inward, the shadow will kind of blur out, so it will be kind of more thicker. So this was this picture solved a lot of these things, but let me back up a little bit to connect it with another stream of development that people had, which is what this tied to. So now I'm talking about a curved space-time, and that, as I said, is the arena for Einstein's theory of general relativity. So the gravitational force enters when we are trying to describe this curved space-time. And so Einstein's equations for the so-called metric of the space-time is a generalization of Maxwell's equations, but it is still classical, and people had tried to understand it at the quantum level, but it led to many infinities. In fact, the usual quantum field theory framework does not seem to work for gravity. And that's usually considered you may have heard of many talks on string theory, where this problem is the thing that people talk about string theory addressing, because it was found around the same time as actually QCD that the excitations of a relativistic string also give you the graviton, the particle associated, like the photon to electromagnetism, the graviton associated to the metric field at the quantum level, and its interactions are finite. So this was a completely different reason why strings were found to be compelling. And for a lot of people, this is a very good motivation. But I wanted to give you here in this talk a very complementary motivation. But you can see how these two actually now tie up, because before that, the rules for, so people had studied then the rules for understanding the interaction of these strings. They generalized the usual interactions in terms of Feynman diagrams in a quantum field theory, which are basically the world lines of particles. Now you have world sheets of strings, these one-dimensional strings. They trace out a two-dimensional surface in time. So you can think of time and space here. You can see these strings are coming in, colliding. They trace out a surface. And this seemed to be, and even now we've learned much more, and it's a right framework for a quantum theory of gravity. So what I've told you so far is that string-like objects arise naturally in both the Yang-Mills theories and in Einstein's theory. I didn't say very much on the latter part, but I was focusing more on the former. And it's this that makes it very natural and compelling. And in fact, the same framework captures both kinds of strings. And this is the preview I gave you of the ADS-CFT correspondence is basically about this, that the equations that govern these flux tubes in at least cousins of the Yang-Mills theories in 4 dimensions are equations of strings in a 5-dimensional space-time, which in certain limits become just Einstein's equations. So Einstein's equations and Yang-Mills theories have a very close connection. This was completely unsuspected, and this is the great insight of the gauge string duality, what is now called, because these are what are called gauge theories and this string theories. So there's a gauge string duality that between these two, and relates very remarkably Einstein's equations in one higher dimension, in 5 dimensions, to Yang-Mills theories in 4 dimensions. Ordinary QCD of the kind that nuclear physicists study every day. And this gave a picture for the quantum space-time of ADS, also a behavior of how space-times behave at the quantum level. It's actually an equivalence. The thing that I showed, maybe, this picture that I showed here, it's actually an equivalence between the quantum field theory on the shadow and this string theory in this quantum gravity in this space-time, this higher dimensional space-time. It's an equivalence between the two. So we have been using it, the string theory, as a way to get insights into the gauge theory, the Yang-Mills theory, but you can conversely use the gauge theory as a way to get insights into the string theory or quantum gravity. And so this is why this correspondence, this ADS-CFT correspondence is so powerful, and people have been really exploring it. And I think even now it's 25 years old, and we have learned an amazing amount of things, but we have still not, I think, fully deciphered it. As I said, it describes the quantum space-time in terms of a quantum field theory in one lower dimension. That's why the name of this hologram. It explains many puzzles and black hole entropy and so on, which is the subject of another talk. But just to give you a glimpse of the power of this correspondence, I'll just end with something which maybe. So this may all seem, and now perhaps the latter part might have seemed very exotic, but actually there's a remarkable connection which I think in coming years will probably also tell us very completely open up completely new ideas for us. As I said, we are still unraveling this quantum, this hologram of this quantum space-time, and it seems that ideas of quantum information and quantum entanglement in that boundary theory are really giving rise to geometry. So there's a notion that's, I think, slowly developing, and people are trying to make more precise in what way quantum entanglement at the fundamental level, you might have all heard of that quantum entanglement is the main reason why quantum computation, quantum computers, quantum cryptography, quantum information is much more subtle compared to classical information, classical computers, classical cryptography. So this quantum entanglement phenomena seems to give rise, we now think, to actually geometry of space-time. And that's what the ADS-CFT correspondence, its meaning seems to be. And these Einstein's equations are in some sense perhaps capturing the flow of quantum information. And these are very cutting edge ideas of quantum information and computing. And I think this is the marvel of theoretical physics. And after 30 years in the subject, I never cease to marvel at how completely new ideas come from left field, so to say. And just so you might never have thought quantum information and computing have much to do with string theory, but nowadays the modern ideas, we seem to be seeing these as very fundamental concepts, which in some ways are giving rise to geometry, and maybe geometry can tell you, like Einstein's equations can tell you new things about quantum information. So this is a very exciting frontier. And since many of you are young students, I thought I should alert you to this. So let me conclude. And though, of course, this is something one can just continue. It's a continuing journey in some ways. So what I try to convey to you is that the lineage, the historical lineage of strings, in some ways goes back to the flux lines of Maxwell and Faraday. And that's the quote of Dirac that I wanted to show you, is in that line, that it's a very natural concept to think of. And in fact, for Yang-Mills theories, it's actually, in a sense, forced on you. Perhaps it was optional in the case of Maxwell's theory, because you had a very good description in terms of Maxwell's equations, and you could describe everything in terms of these fields. You did not need the Faraday picture other than as a picture. But in Yang-Mills theory, in some ways, because of the strength of the quantum effects, these flux tubes seem like the best underlying description. And the surprise of the last 25 years is that these equations governing these strings seem to be the same equations that govern the strings that people have used to study gravity at the quantum level. And these strings appear to be moving in a higher dimensional space-time. And this connection, this remarkable connection between the strings of Yang-Mills theories and the strings describing gravity, which are apparently at first sight seem to have nothing to do with each other, but the fact that they are so intimately connected tells you completely new things. And I just hinted at some of the emergent pictures of a quantum space-time built on ideas of quantum information and entanglement, which giving rise to this holographic picture. So thank you very much. And once again, all the best, especially to all the young students.
Thank you, sir, for the wonderfully illuminating and exciting talk. We may now take up a limited number of questions. So people attending online can type in your questions in the chat box.
Hello.
Hello.
Yeah, great talk. Thank you. So just a two naive questions. So why was this thin string the idealized string? Why?
Yeah, no, it's a bit like when you describe electrons or muons or any of these so-called fundamental particles, quarks, you write down equations for them as idealized point-like particles, because if they have an extent, then they have a substructure. And if they have a substructure, then you have more complications. How are things distributed within that? If I have a proton or even an atom, which people initially thought was an indivisible point-like object, but we now know it's not. It has a substructure, right? So if you are to write, so then to write down an equation for the whole atom becomes very difficult when you're writing an equation for something with a lot of substructure. If you have to take into account, especially when you go to the length scales of the size of that structure, you have to write down, you have to take into account all the inhomogeneities in that substructure. So similarly, if I want to write down the equations for equations for a fat string, you have to know the kind of thickness, the profile of the string, how the tension will vary, etc. It's like writing down the equation for a rubber band. I mean, a rubber band will have a lot of structure, and different rubber bands will behave differently, or a bicycle tube or whatever. They all have substructure. So one expects from one's understanding of fundamental particles that the point-like description, an idealized description, is the one that underlies, perhaps is in some phase perhaps the most fundamental one. And so a thin string, an idealized string in which, just like when you study in geometry, a point has no extent in space. A line has only a one-dimensional extent, a straight line or a curved line. Similarly, a string you think of as, in that sense, having no thickness, only a length. And that is the one that you can describe, write its equations in the simplest way. It may or may not be an approximation, but that is the fundamental assumption, that you write that these idealized strings would be the fundamental description, and those are the ones, in fact, you can write, you can quantize as objects on their own.
Okay, just one more question. So when we assume this hologram for the 4D hologram of the 5D string, so do we expect it to be like a constant in a given pair of quark antiquark, or is it like dynamic, the thickness or the hologram?
Yeah, it is actually dynamic. In fact, that comes to your previous question. That's a good observation. Because if you give the string more energy, in a sense, the fundamental string will become, if you give the string more energy, it can expand, and then it will be dynamical. The picture in the higher dimension is that the very high energy string is actually very close to the boundary. It doesn't go into the fifth dimension so much. It's when you consider the low energy string that you get a really fat string. If you were to look at it at high energies, it actually behaves even on the boundary more and more like a thin string. So the thickness, in a sense, varies with respect to the energy that you're probing it at. So at the highest energy, even in 4 dimensions, you should see a closer approximation to a thin string.
Okay, thank you.
So there is one question in the chat box.
Yes, I can see that. Yes, thank you for the comment on the lecture. Yes, this fifth coordinate is very difficult to sort of understand. It is. You can at one level treat it as a mathematical convenience, that it is a way to visualize the energy direction of the object. I was, in response to the previous question, I was answering that, in a sense, the thickness of the string is captured in that extra direction. So you can think of it in one way as a way of capturing that extra direction, or that it's capturing that the energy scale. You're geometrizing that energy scale into an extra direction. So but at perhaps in some context, that most of the time, that extra dimension will be a very small extra dimension. It will, for the QCD and so on. So in some ways, it's like it is enough to treat it as some kind of a mathematical fiction, because it's a very quantum extra dimension. But in some cases, and I don't think it applies to ordinary QCD, but in some cases, it can appear as a expanded higher dimensional space-time. This would be a very different regime from anything we have seen right now. But there are speculations that maybe that extra dimension is there in our real universe at the time of inflation and so on. So that extra dimension may actually be a real dimension. So that's a sort of a picture of that fifth coordinate that you have asked. So the question was, what is the fifth coordinate in the 5D picture other than our usual space-time? And what happens if the flat space-time is not incorporated in anti-de Sitter space? You can always think of the flat space-time as the boundary of an anti-de Sitter space-time. It is, that's a mathematical fact that you can always think of it in that way. And that seems to be the natural manifestation for this, this picture. So any flat space-time theory you can think of as a boundary of something in an anti-de Sitter space-time.
Okay, thank you. I'm sure you'll have more questions, but due to want of time, we'll move on. Once again, thank you for this exciting talk. I now invite our director, Professor Krishna N. Ganesh, to present a memento to Professor Rajesh Gopakumar as a token of our appreciation from ISER Tirupati for gracing the occasion.
Thank you. Thank you very much. Very nice, very nice memento. Thank you so much for inviting me, and it was a pleasure to be with all of you.
Thank you very much. It was a wonderful talk, and we will arrange to send it to you.
I look forward to that.
Thank you, sir. We now move on to the next item on the agenda, the annual award ceremony of the Institute. We take this opportunity to appreciate the excellence of our students in the academic and extracurricular activities. So we'll begin with the presentation of the CNR Rao Educational Foundation Awards. The CNR Rao Educational Foundation Award was instituted to facilitate the student with the highest SGPA in semesters 1 and 2 of the BSMS program. The award constitutes of a cash prize and a certificate, which would be mailed to the awardees after the program. Yeah, so for semester 1, the award is shared between Anish Mukhopadhyay and Pranav MG. For semester 2, the awardee is R. Vigneshwaran. We next have the presentation of institute awards. Each institute award consists of a book and a certificate, which would be mailed to the awardees after the program. So moving on to the semester awards, for semester 8, the award goes to Divita Balasubramaniam. For semester 6, the award is to Prarthana Agarwal. And for semester 4, the award goes to Ainesh Sanyal. Continuing with the semester awards, for semester 7 of BSMS, the award goes to Shashank V. For semester 5, the award is shared between Ainesh Sanyal and Sanskar Agarwal. And for semester 3 of the BSMS program, the award is to Anish Mukhopadhyay. Next, we have the awards for the integrated PhD program for the batch 2019. The students completed their coursework in 2021, and the award is for the students who have secured the highest CGPA from semester 1 to 4. In biology, the award is to Ramya Vilvadrinath Rajalakshmi. In chemistry, the awardee is Deep Kumar Das. And in physics, the award is shared between Abhik Roy and Sarang Rao Sharma. The next award is for the PhD program for the batch for January 2021. The students completed their coursework in January 2022, and the award is given to the students with the highest CGPA in their coursework. For biology, the award is shared between Abhilasha and Chitti Arvind. In chemistry, the award is Arpita Das. And in physics, the award goes to Tippe Bhushan Harish Chandra. We'll wind up the Students' Award ceremony with awards for excellence in extracurricular activities. And this is recommended by COSA. The first award is to Preet Banjan for the Unnati activities, that is setting up of library in SOS, activities conducted during lockdown times in schools and other colleges, and also for Science Day quiz by Unnati. The award also goes to Nityasri Murugan for the activities during the lockdown, such as lockdown labs, Abhipraknya, and also BioVison activities. Our heartiest congratulations to all the awardees. Let ISER Tirupati be proud of you in the years to come. We also appreciate the services of our faculty and staff members beyond the call of duty. Last year, we have set up the UG lab in our permanent campus, which involved several days of planning, coordination, and continuous hard work from faculty coordinators and our lab technicians, administration staff, and IT section. I invite Dr. Rajesh Vishwanathan, Associate Dean UG, who was the chair of the UG Lab Committee, to announce the names of all those who were part of the huge exercise that led to the establishment of world-class UG labs in our campus. Dr. Rajesh.
Yeah, thank you, Dr. Jatish. Warm regards to everyone here, and especially to our chief guest. So I'm humbled and honored to be standing here to announce the names of the contributors to this success story, which is our UG Labs, as we begin the main campus activities in academics. Professor Ganesh, as the world knows, is a tremendous institute builder, and he has given us the vision and the inspiration to build the labs. And Professor Ambika gracefully set the motion in progress in 2019, setting the motion, the building up of the process. And this has endured through the pandemic days, and we all know how it has evolved. So we have a small presentation with the contributors' slides. I will present their names, and we will go by the division and recognize their contributions. And I would invite you to applaud as the completion of a particular division's contributors are named. So we start with Department of Biology. We have the faculty mentors who have contributed to designing and coordinating the activities that involves Dr. Ramkumar Sambasivan, Dr. Pakala Suresh Babu, Dr. Swaroop Roy Chowdhury, and Dr. Iswar Rami Reddy, and the lab technicians who have tremendously assisted in the process of commuting to the main campus, installing the instruments, testing them, making sure they run with all the constraints that Professor Ganesh also mentioned earlier, is Anup Chandrapal, Mohan Mukesh Malviya, and Tarachan Chopa, and Purushothaman Mabbu. So, and for Department of Chemistry, we have faculty coordinators who have been mentors designing the labs with Dr. Pankaj Kumar Kohli, Dr. Sudipta Roy, Dr. Arun Kumar Bar, and Dr. Kiran Kumar. And they've been ably assisted and well coordinated between Kata Vamsi, C. Geeta, Sujata Kata, and Satish Mutyam. And for the Department of Physics, we have Dr. Chitrasen Jaina and Dr. Dilip Mampalil and Dr. Sunil Kumar, who have been the mentor faculty to design the labs and aid in assisting and planning this with the lab technicians. And the lab technician contributors are Mr. Alastin VP, Kolli Nagarjun, Dr. Sivaraju Donempudi, and Vankara Pradyamnu. And all of this would not be possible without the leadership of Dr. Mohan Kumar, our registrar, guiding us with the administration section of setting up the labs. And we have Nandam Jaisurya, who has contributed to purchase and installation of all the instruments and equipment that's needed in the main campus. And we had from IT for ably assisting in all the classroom activity, as well as the coordination of the instruments, Satish Jadhav and Arun Sairam. And of course, we very well know our engineers from day one of the Institute, Anthony Joe and Shivakumar Kuna. And we especially thank Inderpreet Singh Kohli and his team and the housekeeping staff for all their efforts in relocating the UG lab. And especially considering this was all done through the pandemic days, it makes our effort even more recognizable and special. So thank you so much. And PVNR Rao Garu also for assisting the leadership on setting up the labs there. And with that, hearty congratulations to all of the contributors. Let's move ahead with the plans for the academic research building. And with that, I thank you all once again, and let's give a round of applause. Thank you.
As we come to the end of the ceremony, I request our registrar, Dr. C.P. Mohan Kumar, to propose the vote of thanks, which will be followed by the national anthem.
Good afternoon. As stated by our chief guest and our director, Foundation Day is a good time for a nascent institution like ISER Tirupati to reflect both on its progress thus far and journey to achieve its goals and vision. It's also an opportunity to showcase the institution and encourage more students to take up a career in scientific research and teaching. On this occasion, we are indeed privileged to have with us Professor Rajesh Gopakumar, Director, International Center for Theoretical Sciences, Bengaluru. We sincerely appreciate his acceptance of our invitation, making time for us, and delivering his talk on wise strings. I'm sure, sir, that your talk would definitely inspire and kindle more interest in the young minds to take up science as a professional research or teaching career. Science and its capabilities and importance in saving lives was evident during the last 2 years of the pandemic. Thank you very much, sir. Institution building is both a science and an art and takes deep thought, a long-term vision, and sincere commitment, coupled with a humane and altruistic approach to administration. We have been most fortunate to have such an institution builder in our director, Professor K.N. Ganesh, who first as a mentor director and then as a regular director has continued to guide and lead us. Today's milestone and the many more to come will rise from the foundations of leadership and governance laid by Professor Ganesh. Thank you, sir, for being there for us, guiding us, and nudging us all to reach higher levels of performance and achievements, and also presiding over today's function and giving your introductory remarks. We wish to thank Professor J.B. Joshi, our eminent chairperson, Finance Committee, and Board of Governors, and all the members of the Board, Finance Committee, Senate, and the Building and Works Committee for their constant support and guidance. Our thanks are also due to the Secretary and Additional Secretary and other officials in the Department of Higher Education, Ministry of Education, Government of India for their support. Faculty, staff, students, and parents form an integral part of this institute's progress, and we today acknowledge all their efforts and contributions to the growth and development of the institute. Our deans, chairpersons, academic coordinator, associate deans, continue to contribute significantly despite challenges of operating from 2 campuses and in a hybrid mode. We specifically acknowledge the contributions of all the faculty, technical, administrative, contractual, security, and housekeeping staff for their efforts in making the UG lab and hostels in the permanent campus operational in record time, despite the challenges posed by the pandemic in logistics and material supply chains. Also, thank all our partnering institutions on this. I once again congratulate all the awardees and thank you one and all for joining us online and in person. Thank you very much.
I request you all to rise for the national anthem.
तब शुभ नामे जागे, तब शुभ आशीष मांगे, गाहे तब जय गाथा। जन गण मंगल दायक जय हे भारत भाग्य विधाता। जय हे, जय हे, जय हे, जय 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 हे।
Thank you. Thank you all.
Thank you, everyone, and bye-bye. See you all later.